Today I'm going to teach you about feedback resistors in DC to DC converters, and I'm going to show you how to use this knowledge to build an adjustable power supply with an output voltage between 2.5 volts and 14 volts. So in a previous video, I showed you how to make a 5 amp buck converter with a 5 volt output. I told you that these resistors configure the LM2678 to have a 5 volt output. Let's talk more about how this works. Most DC to DC converter controller chips have a pin called the feedback pin. This is the part of the chip that's used to monitor the output voltage. The controller basically looks at the voltage on the feedback pin, and if the voltage is too high or too low, it adjusts the pulse width of the switching waveform, which then gets filtered, and the correct output voltage gets restored. In this example, I have a 10 volt input going to the supply, and the load is changing between half an amp and 5 amps. The feedback mechanism takes care of this, adjusts the duty cycle, and a perfect 5 volt output gets maintained. Let's talk more about how this works and how we can design our own feedback resistor network. DC to DC converter controllers usually have a precise internal reference voltage called VFB. The exact value will depend on the chip you're using, but it will always be given in the datasheet, and it's usually around 1.2 volts. For our LM2678, it's 1.21 volts. If we got rid of the feedback resistors and connected the output of the supply directly to the feedback pin, the controller would look at the output voltage, compare it to 1.21 volts, and then do whatever it has to do to ensure that the output stays at 1.21 volts. But that's not very useful, is it? Why would you want to use a 1.21 volt supply? Okay, let's add a 10-to-1 voltage divider here. So whatever the output voltage is, it gets divided by 10, and that's what the feedback pin on the controller is receiving. This effectively multiplies the output voltage by 10, and you get 12.1 volts on the output. So we're dividing, but we're multiplying, which is a little weird, but check this out. Let's say the output of the supply was 12.0 volts. This gets divided by 10, and the controller would see 1.20 volts on the feedback pin. The controller would then say, hey, this is too low. We need to increase the output voltage. So it increases the pulse width and raises the voltage to 12.1 volts again. The controller sees 1.21 volts on the feedback pin, and now it's happy. Now let's say there's a sudden drop in the output current, and the output voltage shoots up to 12.2 volts. The controller would see 1.22 volts. The negative feedback control loop inside the chip would then reduce the duty cycle, restoring the desired output voltage of 12.1 volts. And by changing the values of the resistors in the feedback resistor network here, we can set the output voltage to be pretty much anything we want, assuming all the components can handle the extra voltage. You can use these formulas to set the output voltage to whatever you want it to be, within the limits of what the controller chip is capable of. You can also have a little bit of fun. If you make these resistors fixed and also add a variable resistor, you can create a variable output voltage power supply. Now you have a step-down power supply that can output 2.5 volts to 14 volts DC. Right now I have my power supply set to 13.8 volts, and I'm using it to charge a 12-volt lead-acid battery. I can use this supply to dim LEDs, power amplifiers, or just see how much voltage something can handle. Now, if you remember my video about voltage dividers, I talked about how it's the ratio of resistance values that determine the voltage. If that's the case, why not just use these resistor values? If you think about it, this would reduce the power consumption of the circuit, but there is a trade-off. Our switch mode power supply is switching high currents at high frequencies. Whenever you do this, your circuit will put out some electromagnetic interference. You can see this for yourself with a cheap AM radio. The electromagnetic interference is inducing small currents into the antenna of my radio, and it's getting picked up as unwanted noise. Now, there's a difference between how electric and magnetic fields affect things, but I'm just trying to keep things simple here. Things get really interesting when you realize that the switch mode power supply can actually interfere with itself. Let's say some interference from the inductor reaches the feedback resistors. This will induce a tiny unwanted current in the resistors. When you have current flowing through a resistor, a difference in voltage gets created. Because volts equals current times resistance, the higher the resistance, the higher the unwanted voltage you get in the form of noise. And this can affect the controller's ability to regulate the output voltage. In general, you want to keep the total resistance of your feedback resistors somewhere between a few kiloohms but under 1 megaohm. This will minimize the amount of noise in your power supply that's created by interference. This is also why I like to work on high-powered electronics with my oscilloscope probes set to X1 attenuation. The lower resistance makes them less susceptible to interference. Alright, now you know what feedback resistors are, and you can use this knowledge to change the output voltage of almost any DC to DC converter. Just make sure you double-check the voltage limits of your capacitors, diodes, MOSFETs, and so on, according to the design guidelines of your controller's datasheet. Sometimes overclockers use this trick on their video cards and motherboards to change the power supply voltages to achieve higher clock speeds. Or if you want to save power, you can run things at lower voltages. Thank you for watching, and if you enjoyed this video, please check out the video description section to see how you can support me. Make sure you check out Patreon, which is a way you can donate money per video to keep the channel going.